Thank God. Yeah, yes, I think this is working okay. Right. Okay, so good morning. Welcome to, although it says lecture 2 here, this is of course the third lecture of the computational complexity course. I'm starting with lecture 2 because I want to begin with just a brief revision to what we did last week and a couple of corrections to the definitions in the notes. But before doing that, just to say, so as I said at the beginning, my preferred style of lecturing is to write on the whiteboard and to lecture with the whiteboard. But 10 days ago, I had a little operation, as I said last week. I'm still supposed to be resting my shoulder. So today I'm once again going to give the presentation sitting down using my tablet. I don't know if it's better or worse for you, but I prefer to normally write on the whiteboard. The benefit of presenting things using the tablet is that at the end we get notes, and I publish the notes online. So we're going to begin by just briefly remembering what we did last week with a few. I want to point out one thing and also make a couple of small corrections. So last week we introduced the model of computation, which is going to be the model we use throughout the course, the model of Turing machine. So I motivated that with the design criteria. I described what a Turing machine is by giving an example in the exercise class last week. Anyway, you did plenty of playing around with Turing machines. So you're now very familiar with the notion of a Turing machine. The mathematical definition of a Turing machine requires saying what the alphabet is for the tape, what the states are, and what the transition function is of the Turing machine. Once we've got a Turing machine, we know how to execute it. And importantly, we had this notion of a Turing machine as a language recognizer. So the input to a Turing machine before we run it is a word over an alphabet. That's a sequence of symbols from the alphabet. And the Turing machine is a language recognizer. We're mainly going to use Turing machines in this way. We input a word and we want to see whether the Turing machine accepts or rejects the word. So we have Turing machines, and when we input a word, we want the Turing machine to compute. We want the Turing machine to always eventually terminate in one of these two states, either we accept the word, or we reject the word. And we say, very importantly, that a language, that is a set of words, is decidable if we can construct a Turing machine such that whenever we give it an input word, it accepts the word whenever that word is an element of this language set, and it rejects the word whenever the word is not an element of this language set. So whether or not the Turing machine accepts or rejects, we can use the Turing machine to tell us whether or not the input word belongs to the language set. And the important thing I've added since last week, I said this on the last slide last week when I was describing it, but the terminology, we say that the Turing machine M decides the language L if it does this. So if the Turing machine M, so L is a language, it is a set of words. And if the Turing machine behaves in such a way that when we give it a word over the alphabet, the machine will accept that word if and only if that word belongs to L, and will reject the word if and only if the word does not belong to L, then we say that machine decides the language L. So we can use the machine to test whether or not an input word belongs to the language L. Okay. So that's one way we use Turing machines. Another way we're going to use Turing machines is to compute functions. So for a Turing machine to compute a function, we give it an input word on the tape. The Turing machine computes away. We want it to halt. And when it halts, we look at the output word that the Turing machine has written to the tape. And the function that the Turing machine computes is the function from input words to output words that Turing machine enacts in that way. As somebody said last week, there's no reason to have the input alphabet as being the same as the output alphabet here. Both the input alphabet and the output alphabet have to be subsets of the tape alphabet because the input word has to be written on the tape, and in the end, the output word has to be written on the tape. But on the other hand, I think I need to put this control bar down at the bottom. But on the other hand, we can ask for it to input words from one alphabet and output to another if we want to. So let's actually make that generality. So we just have some alphabet sigma 1 for the input and some alphabet sigma 2, and they can be the same. Okay, so that's a little generalization of what we did last week. So then we looked at various notions of variations on the notion of Turing machines, for example, well, in particular, machines with several tapes and several heads, typically one head per tape. And once again, you looked at this in the exercise class last week. This variant is going to be particularly important. So we have the one tape Turing machines, single tape Turing machines that just have one tape, and the multi-tape Turing machines that have some number of tapes and one head per tape. But they're all kind of equivalent to each other in that whatever variation we choose, we can transform any such variation back to a single tape Turing machine. However, when we do that, there might be a little bit of a loss of efficiency. So I think you did this last week in the exercise class. You translated, hopefully by the end, you translated a multi-tape machine to a single tape machine, and you hopefully found out that the runtime could grow quadratically when you do that. Okay, so single tape machines are quadratically slower than multi-tape machines. But a quadratic blow up, we're squaring the execution time, that's still polynomial. So the translations between machines only involve at worst polynomial factors of change of time, and that's going to be important. So we had an example 2-tape language machine last week, and I asked you a question, what language does this recognize? I don't know if anybody looked into that, but the language was palindromes. So those words that are the same forwards, the same if written forwards as if written backwards. So when we looked at the Turing machine simulator at the end of the lecture last week, we saw a 2-tape Turing machine for palindromes, but that was actually using a slightly different algorithm, a very slightly different algorithm from this one. Okay, so those are multi-tape machines, single tape machines. We can translate between them. We have only we have at worst a quadratic loss of efficiency when we translate from a multi-tape machine to a single tape machine. And then we get to the important definitions of this course. Well, some of the important definitions in particular, I ended the lecture last week defining the notion, the class of functions, sorry, the class of problems P, those problems that we can decide in polynomial time. But there's actually a little flaw in the definition I gave last week. A flaw, this is FLAW flaw, like a little error in the definition I gave last week, which is, so n here is the size of the input string, and we're asking here for, so this is saying a problem is in polynomial time if any input string if we have a Turing machine that decides the problem such that for any input string, if we run that of length n, if we run that Turing machine on any input of length n, the time taken for the execution is at most c times n to the d. The problem is, it's a very silly little problem, but the problem is when, well, for some constant c and d, the problem is that when n is 0, c times n to the d is always 0. And that's saying when we give it the empty word as input, the Turing machine needs to decide it in 0 steps. But in order to decide it, the Turing machine needs to go from the start state into the accept state or the reject state. So it needs to take at least one step on the empty string. So at the moment, it's a very, very silly little problem. But at the moment, if one takes this definition literally, there are no problems at all in P because the empty string, there is no Turing machine that will do the right thing on the empty string in 0 steps. So it's a very tiny problem. It seems to me that the definition in the textbook has the same problem. So maybe I'm missing some subtle point somewhere, but it seems to me that the textbook has the same issue. So we want to correct this. I'm going to actually correct it by giving the definitions in the way I would like to give them, and also by emphasizing that I did actually make a mistake in the definition of deterministic time last time, because the constant factor here is supposed to be in the definition of deterministic time. So let me just start this sheet again, and I'm going to re-give the definitions in the way that I think is the best way to give them. And it's basically going to give the same definition of P as before, having corrected it with this issue of that it didn't work it didn't work because of the problems with the empty input, which is obviously a bit of a trivial issue. So the way I'd like to do things is I'd like to say that I'd like to use this way of doing. So I think the more intuitive definition so if M is a Turing machine, we define the function, time function, which times the Turing machine. I've used this with a little t, time sub n, which is a function on natural numbers. And this is simply the function that counts the number of steps of the slowest Turing machine on it. So given an input length n, it counts the number of steps of the Turing machine, of the worst case Turing machine for this Turing machine M, running it on inputs of length little n. So in other words, time of the Turing machine, the time taken by the Turing machine, the worst case time taken by the Turing machine on inputs of length n is the worst case. So it's the maximum of over the set of the number NO dot in English is abbreviation for number. So the number of steps taken by the Turing machine, by M on input W. So we require the Turing machine to halt on all inputs on input W. This is the maximum over the set of all words W in the input alphabet whose length is n. Okay. So the worst case running time on inputs of length little n. And now the deterministic, now we want to say what it means for a language to be in a particular deterministic time class given by a specified function, Tn. So for example, this function might be n cubed, and we want to say what it means for a language to be in deterministic time n cubed. So intuitively, that should mean there is a Turing machine whose runtime is big O of n cubed. And that's exactly how we're going to define it. So for a language and a function, we want to say the language can be decided in deterministic time t of n if there exists a Turing machine that decides, so let's say a Turing machine, let's give it a name, M, that decides L such that, and what we want is that the worst case runtime of that Turing machine is big O of the function t of n that we're giving. So such that the worst case runtime, such that the runtime of that Turing machine for inputs of length n is big O of this function t of n. And let me just put the annotation here. This is, remember again, this is the length of the input W. So the difference before is that now, well, we're not worrying about the zero case because we're using big O here. So big O of a function, as you'll remember from the first lecture and exercise classes, it just means that eventually we're bounded above by a constant, eventually the function on the left is below a constant multiple of the function on the right. So we ignore initial cases here, but the other important point is that here, because we're using big O, there's a constant factor on the right-hand side here. So if we're big O of n cubed, for example, that means the runtime could be 427 n cubed, or it could be 653 n cubed. It doesn't matter. Any function with that sort of runtime is still going to be in deterministic time n cubed. Okay. And now the fundamental definition is still correct, which is, but now we don't need to put the constant factor in anymore because the constant factor is already in the big O above. So now P is just all those problems that we can decide in some polynomial amount of time. So we can just use monomials because we're using big O. And so it's either in linear time, that's d to the what, d equals 1, quadratic time, d equals 2, cubic time, d equals 3, and so on. Okay, there's one other important thing to say here that I forgot. Is that it's important in the definition of deterministic time, it's actually important in this definition that our Turing machine here is a multi-tape Turing machine. For example, the problem of whether a string is a palindrome or not, that is in deterministic linear time for multi-tape Turing machines, but it requires quadratic time for a single tape Turing machine. So if we specified a single tape Turing machine, if we required a single tape Turing machine, then we would get a different complexity class. What's normally taken to be the definition of deterministic time is for multi-tape Turing machines. So being a palindrome, we think of that as a linear time decidable problem. But we do, to get that with the Turing machine model, because to check something's a palindrome, you can do that in linear time. You just need to go left to right through the string in both directions. So we can do that in linear time, but in order for that to work out with the machine model, we do need to use multi-tape Turing machines. When we come to the definition of polynomial time, however, it doesn't matter if we restrict to multi-tape Turing machines or to single-tape Turing machines, because here we're saying any polynomial in the runtime, and because there's a polynomial time translation between multi-tape Turing machines and single-tape machines, for this definition of polynomial time, it doesn't make any difference. Okay, so that's the review of last week's with a correction. Are there any questions on that?
Is the d in the power of n here also non-integer? Can it be a non-integer?
It could be if you wanted it to be. I mean, if you make d a non-integer, it's the same definition, because you could, if d is 2.7, then you could put d equals 3, and any problem that works with d equals 2.7 will still belong to the class with d equals 3, because we're just asking for upper bounds on the runtime. So we might as well just restrict to d being an integer in this case. So the function Tn, I'm sort of assuming it's natural numbers to natural numbers here, but it actually doesn't matter. And in fact, sometimes we will use functions like logarithm and not worry too much that returns a real number as an output, that logarithms are really real valued functions. And if you want to turn them into an integer, you can take the floor or the ceiling if you want to. But we're not going to we just won't worry too much about that. Okay, so that was last week's lecture, and now having corrected the definition, let's go on to lecture 3. Oh, which is and today's lecture is going to be about slight modification of the model that's not equivalent to what we had last week, which is non-deterministic Turing machines. And we're going to use those to define the other half of the famous open question, does P equal NP? We've defined P, the polynomial time decidable problems. And we're now going to define NP, the non-deterministic polynomial time decidable problems. So by the end of today, we're going to know what the question, does P equals NP mean? A question that has $1 million prize for its solution. So what is a non-deterministic Turing machine? Well, let's again begin with an example. So here's the example Turing machine from last week. And let's turn it into a non-deterministic Turing machine. Yes? I've already closed mine, so I'm very happy for anybody to close. It's really quite cold in here. It depends on if we're all happy for that. Yeah, I mean, we're supposed to be airing the room as much as possible, but it's not the warmest day. So an example non-deterministic Turing machine. So this is last week's Turing machine. This was the Turing machine that decided the language of words that alternate their characters. So if it started with A, it needed to go A, B, until it finished, and vice versa. And it was deterministic because in any state, in any configuration of the Turing machine, with the head in a certain position and the tape in a certain tape configuration, there's at most one transition you can make. It's configured like this. Whenever we have a particular state and a particular symbol that the head is looking at, there's at most one step we can do to get to the next state. So non-deterministic just says there may be more than one transition we can make. So I'm going to make this machine non-deterministic by adding, let's put it in red because we're adding it. Make it clear that what we're adding to last week's. So I'm just going to add another transition from next day and B. So when we're in state next day and we're in B, we can either go into reject, or I'm going to allow us to, instead of going into reject, to stay in next day, keep the B on the tape, and move one place to the right. So I'm just adding one more transition, but it's now a non-deterministic machine because when we're in state next day and we see the character B on the tape head looking at a character B, then there are two possible things we can do. So it's non-deterministic. It's not determined what happens. So I'm going to be rather quick about this, but let's look at two runs. So let's going to run it on the tape ABB. So we're in the start state, and we start with the head at the left end of the input. But rather than what's the word I'm looking for? Rather than animating it on the machine itself, I'm just going to write down the lists of configurations we go to in a sort of shorthand on the right. So we're starting in the configuration start with ABB on the tape, just blanks everywhere else. So we can write ABB for the tape configuration and with the head on the A. So I can just write the configuration that we start off in like this. Then I want to write it in two different places because we're going to but basically I'm executing the machine starting off in this configuration here, and this is just a shorter way of writing the configuration. Because we're in start and we see an A, we move to next B, with the head moves to the right and we keep an A on the tape. That's the only thing we can do. So we move to next B. And we keep the A and we move the head to the right. So we go to ABB. And I'll write that down here as well. Now we're in both configurations. So here we're running the machine and here we're running it again. In both configurations, we're in next B and we're seeing a B. And again, there's only one thing we can do. We can go to next A and keep the B on the tape and move to the right. So we go to next A. Keep the B that we're looking at on the tape and move to the right. So the head moves to the right. So this is a little triangular head, by the way, if you can't see what I'm writing there. I hope it's clear. Let me know if you've got any questions about this. So we're going to next A, and we've got A, B, B. Okay. And now in this configuration, we're in next A and we're looking at a B. And this is the configuration where we've got two different transitions we could take. So from next A and from state next A looking at a B, we can either do what we would have done with the deterministic machine we had last week. So that goes next A and B. It can go to the state reject. It keeps the B there. And it doesn't move the head at all. Alternatively, if we've got next A and we're looking at a B, it can also go to next A, can stay in next A. So it can stay in next A. Keep the B on the tape, so we A, B, B, and move the head to the right. So on the right, we've got a blank. And we move the head to the right. So here we're in the reject state, and there aren't any transitions from the reject state, so the machine has terminated. Here we're in the next A state, and we're looking at a blank, so the machine keeps on computing. If we're in next A and we see a blank, then it goes to accept. We keep the blank, and we keep the tape head where it is. So the tape configuration is still this. And now we're in the accept state, and again, the machine terminates because that's a terminating state. So what we see is the non-deterministic machine running it on the input ABB. There are two different possible ways it can execute in this case, and they give us different answers. One way says reject, and another way says accept. And what we call this is two runs of the machine. So this is two different runs. So when we run a non-deterministic machine, we don't know what's going to happen. That's why it's non-deterministic. It's not determined of the machine. Okay, so that's one example of a non-deterministic Turing machine. So in general, if we're defining a non-deterministic machine, what do we have to change? If we're specifying a non-deterministic machine, what do we have to do that's different from specifying a deterministic machine? So to specify a non-deterministic Turing machine, so I'll say, oops, I want that to be black. And a non-deterministic Turing machine. I hope you can see that says, maybe I'll write it a bit clearer. So an ND Turing machine is specified by Well, we basically give the same information in terms of, we again need a tape alphabet. We again need a finite set of states. It's all as before. The difference is that our transition function is no longer a function. A function is like a deterministic thing. You give it an input and it gives you an output. I mean, before the transition function was a partial function in that from some states and tape symbols, there was nothing that it would do. For example, from the terminating states, the accept and reject states, there was no transition out. But when there was a transition out, there was only one transition that we could take. For a non-deterministic one, there might be several. So the appropriate mathematical thing here is a relation. Or a relation from, if you like, a relation from pairs consisting of the current state and the current symbol that we're looking at on the tape, a relation between that set and the set of information that we change to, which is again a state, a symbol, the symbol that we're rewriting over the old symbol, and the head movement. But to define a relation between two sets, so here this product set of two things, the state and alphabet, and here the product set of three things, that's the same thing as giving a subset of the product of everything. So let's just put it in that simple form. So it's a relation, but we can just write this as a subset. And typically one uses a little delta for a transition function. But now we've got a transition relation that there might be many different things we could do. One traditionally uses a capital delta for this. So I'm going to call this delta, capital delta, and it's a subset. I'll still often call this the transition relation. Sorry, oh. I seem to have clicked on the wrong thing. So it's now a subset. And because it's product of sets, one doesn't need to bracket it in any way, but let me just put blue brackets here because I'm going to think of it as bracketed here in this way, that these two components one thinks of them as lying together because this is the state we're currently in together with the symbol we're currently looking at. And this triple here is the state we're going to move to together with the symbol we're going to write over the current one together with the direction we're going to move the head. And this is called the transition relation. And so whereas before, for every current state and tape symbol, QA, there was at most one new state, new tape symbol and displacement. There is now any number of, including 0. So there are any number of, potentially any number of new triples we can go to of the new state, new symbol and displacement. So such that QA together with Q prime, A prime D, this pair belongs to the transition relation delta. And again, I use this notation that from the current state Q and current symbol A, we move to the new state Q prime and new symbol A prime with the head displacement D. And again, a machine configuration is just as before, a triple. So when we run the machine, so I was writing our configurations here. So this was a run of the machine. We go from the start configuration we make a step to the next configuration, then another step to the next configuration, and so on. So again, these configurations are again triples consisting of a state, the tape configuration, so here written just briefly as ABB, but it means a blank everywhere to the left, blank everywhere to the right, and the head position, which I'm writing just as part of the same information here, just writing the triangle. They're giving that mathematically, we can write this as before. Formally, a machine configuration is a triple consisting of a state, the tape configuration, and the head position. And so I is the head position. And we execute the Turing machine as before by starting it in the start configuration, making transitions from one configuration to the next configuration. But the difference is that now at any step in that process, there may be, we're in some configuration, there may be more than one possible next configuration we can move to. And so now we have the notion of a run of the Turing machine. And even if we give the non-deterministic Turing machine the same input, there might be several different runs on that input due to taking different non-deterministic transitions as we make the executions. So we've got the important notion of a run of a non-deterministic Turing machine starts in the start configuration and makes a sequence of possible successor transitions. So we go from one configuration to the next configuration, to a possible next configuration, and then from that configuration to a possible configuration that follows that. And so on. Until, if ever, it may run forever, a terminating configuration is reached. I'm trying to avoid being too formal here about the notion of what a run is. But the point is, a run is a sequence of configurations starting in the starting configuration, where at each step we make a legal step of the Turing machine, and we keep on doing that until we get to a terminating configuration. And if we don't get to a terminating configuration, then it's an infinite sequence of configurations. So the point is, if we run a non-deterministic, the important point is a non-deterministic Turing machine may have several possible runs on the same input. Let's say many, actually, many. I guess in Slovene it's probably similar, but different words for a number of things have different. Several sounds like a bit fewer than many. So we want to really emphasize there were only two in the case we were looking at, but actually non-deterministic Turing machines have really a lot of possible runs, surprisingly many, because it's somehow potentially exponential in the number of steps you take, the number of runs. So they have many potentially possible runs on the same input. Okay, so I think that's a good stopping point. We'll resume at 1/4 past. Let me just stop the share and pause the video. Right, so we've seen what a non-deterministic Turing machine is. So in general, we have more than one possible transition we can take out of the current configuration. And we don't know, if we try to run the non-deterministic Turing machine, we don't know how it's going to be decided, which transition will take. With a deterministic one, it's easy. The machine takes the only transition that is possible. With a non-deterministic one, who knows how it's decided which transition is going to be taken. So there's something, it's not in that way very satisfactory as a model of computation, because at the moment, as specified, we don't quite know how it will execute. But nonetheless, as a mathematical definition, it makes sense. And what we're going to see now is how we can adjust the definitions of Turing machine recognizing a language to non-deterministic Turing machines. So how are we going to say, if we look at what language a non-deterministic Turing machine can recognize? So how can we make the definitions? So we're interested now in running a non-deterministic Turing machine on input words and seeing whether or not it accepts or rejects the word. So we're going to look at non-deterministic Turing machines. So ND is going to be short for non-deterministic or non-determinism. And so NDTMs is short for non-deterministic Turing machines. So as before, we're going to run a machine on words to try and accept or reject them. We're going to, again, require that we have the input alphabet that the words are written in. Is it okay if I shut the door, actually? Is that...
And we're all boxed in.
For the sake of peace. So again, to look at whether or not we accept words, we're going to fix the alphabet. So we assume we have some alphabet for our input words. And again, we want to either accept or reject a word. So we're going to ask for the distinguished halting states that the machine will halt in, accept and reject. And now we want to say what it means for a non-deterministic Turing machine to accept or reject a word. So we need to model. So these are the definitions as before. So let me just, it's not very much space, but I think I'll give myself some more space. So if we change this to a non-deterministic Turing machine, we want to say it accepts a word. So let's see what happens if we use the old definition. If when we run the Turing machine on the word, so this is the old definition for a Turing machine, a deterministic one, when we run the Turing machine on the word, the computation ends in accept. There's a problem with this definition because the example we saw before, our very simple example of a non-deterministic Turing machine, we ran this in two different ways on the same input word ABB, and on one of the runs it said reject, and on the other run it said accept. So we might get conflicting answers. So we need to give some way of saying what it means to accept a word that's unambiguous. So what we require, so I'm going to just create some more space here. So to accept a word, we say the non-deterministic machine accepts the word if there is some run that returns accept. It doesn't matter if some other runs say reject, that's just a bad answer. As long as at least one run says accept, then we accept the word. So let's just create lots of space So if there is some, there exists, in other words, so if there's some run of the NDTM on input word W that halts in accept, in the accept state. And similarly, it rejects, or rather not similarly, but we want every word to either be accepted or rejected. So to reject a word, we need to require that there is no run that accepts, but we want to always get some answer out from our runs. So in other words, we're going to require that every run of the Turing machine on the word rejects it. Okay. So it rejects double. So it's an asymmetric definition. It's not like with a deterministic machine, we can easily change to the complement of the language by just switching the accept and reject states. But for non-deterministic machines, it's an asymmetric definition. To accept a word, we just need some run that accepts it. To reject a word, we need that all runs reject it. So if every run of the NDTM, non-deterministic Turing machine, on input word W halts in reject. And once again, we're going to use these to say what it means for a non-deterministic machine to decide a language. So again, we're interested in looking at sets of words. Is the word accepted or is the word rejected? So we say, non-deterministic Turing machine. So I'm writing the AN here, so it's a non-deterministic Turing machine. I'm writing the AN because it's an NDTM, if one wants to pronounce the acronym as a word. So an NDTM decides the language L, so that's just a set of words over the input alphabet. If, let's call the non-deterministic machine M, if M accepts every word in the language, and it rejects every word that's not in the language. And rejects every word not in the language. Okay, so it's a small adaptation of the same definition for deterministic machines, in that if M is a deterministic machine, it's the same as before, because all these definitions are the same. If you've got a deterministic machine, there is only one run. So that run will either accept or reject, and we've got the same definition as before. But if we have a non-deterministic machine, we've now got a more general definition of accepting and rejecting, and a more general definition of deciding a language. Okay, so like last week I gave you a question of what is the language for the multi-tape machine? What is the language that is decided by the machine that the example multi-tape machine we had last week? So here I've modified. Remember this when this was an ordinary deterministic Turing machine. This Turing machine in black here accepted those words that consist of alternating characters. I've now modified it by adding one more transition. So this is an exercise not for, well, you can solve it immediately now, but I'm not going to keep the definition on the board. That's fine. Otherwise, you can think about it after the lecture. The question for next week is what language L is decided by this. So it's a set of words by this non-deterministic Turing machine. Okay. So it's all been, everything has been quite abstract so far. So I think maybe before going on the next abstract thing I want to do is now modify the definitions we had for running time. In fact, maybe I'll do that because that's going to be quick, and then we'll go on to an example. And then I want to go on to an example. So we've got some example to hold on to rather than all these abstract definitions. But let's, having said what it means for a non-deterministic Turing machine to decide a language, let's just now adapt the notions of adapt the definitions of running time and deterministic time and P to give analogous non-deterministic definitions, and the analogous non-deterministic definition of the languages that are recognized in non-deterministic polynomial time are going to be exactly the languages NP. So then we'll know what the NP equals NP question is, and then we'll look at an example. Well, then we'll start to look at many examples. So let's just make the modifications of runtime and so on to non-deterministic Turing machines. So this is the same these are the same definitions that we had just from the beginning of the lecture, and I modified last week's. So now I want to modify the notion of runtime for a non-deterministic Turing machine. So again, the time function of that non-deterministic Turing machine is going to any number n, is going to assign, we're going to assume the non-deterministic Turing machine, whatever choices it makes, it always terminates. So that's in the background. I should have said that more explicitly, perhaps on the slide, but I'm saying it out explicitly out loud. So we're assuming the machine terminates. And before, for deterministic machines, the time of the machine on inputs of length n was the worst case runtime over all the inputs of length n. And we're going to adopt exactly the same definition. Again, the worst case runtime. But now there's the difference that it's not just worst case over all the inputs of length n, but it's also over all the different runs on all the inputs of length n. So on every input of length n, there might be many different ways of running the machine, and we want to look at the worst case runtime over all possibilities. So it's now so let's see how we can modify the definition. So the time of the non-deterministic machine M on inputs of n, so we want to take the maximum over all runs. So let's do it like this. I'm just, oops. So taking the maximum over all input words of length n, and let's even have a word R. R is a run of the non-determinist of M on input W. So we want to take the maximum over all input words of length n and all runs on the input word W of the number of steps in R, in the run R. Okay. And now we can say that a language is in non-deterministic time. I think it's just n time. I should check that in the textbook. So I may this is either nd time or n time. I'm pretty sure it's n time, but I've forgotten. And by the way, if you're looking at the text, I mean, the textbook has all the material there, but you might have noticed the way of presenting it's a bit different. So, I mean, the textbook I want this textbook because it's got all the material for the whole course in, but as I said at the start, I'm going to present things sometimes in my own way. But anyway, a language is in non-deterministic time t of n. So this means if non-deterministic, again, if there exists a multi-tape, non-deterministic Turing machine that decides the language L such that the time of the machine is big O of t of n. Okay, so the same definition, asymptotically, a constant multiple of Tn is an upper bound of the worst case runtime over all possible runs for inputs of length n of the machine. And the fundamental definition of NP is simply change deterministic time to non-deterministic time. Okay. So if language is in NP, if there exists a non-deterministic Turing machine that decides that language, it accepts a word if and only if it belongs to that language, rejects the word if and only if it doesn't belong to the language, and that machine runs in time that is bounded by, so it's worst case runtime over all inputs of length n and all runs on the input is bounded by some polynomial in, well, some polynomial in the size of the input. Okay. And the big question is whether the class P is equal to the class NP. So let's first make an observation, and then we'll go on to the definition. So the observation, so P is a collection, it's a set of languages, that's a set of subsets of the alphabet, of the words over the alphabet, sigma star, so a set of sets of words. So a language, a set of words is either in P or not. Similarly, NP is a set of sets of words. It's a collection of languages. And the observation is that every language that's in P is also in NP. So the class of languages NP is larger than the class of languages P. Every problem that is polynomial, deterministic polynomial time decidable is non-deterministic polynomial decidable. The reason for this Well, can anyone tell me what the reason for this is?
Follows from the definition.
Well, it does follow from the definition, but why does it follow from the definition?
Because every deterministic Turing machine is also a non-deterministic.
Exactly. So every deterministic Turing machine is a non-deterministic Turing machine. And for the deterministic machines, these definitions, the time M definition is the same, and the definition of deciding a language is the same. Whether or not you take the non-deterministic definition or the deterministic definition, they both coincide. So because every deterministic machine is trivially a non-deterministic Turing machine. Trivially in the sense that it's got trivial non-determinism. Okay, and while we've got this question, let me just flag it. You can think about this if you want to challenge. I mean, we're going to look at this question in more detail anyway. My writing seems to be getting messy. So the open question is, does the other inclusion hold? And if the other inclusion holds, of course, there's an equality. So the question that's normally asked is P equal to NP? Or actually, people often say P is not equal to NP because the conjecture is, so it is widely conjectured that they're not equal. And actually, for a course like this one on computational complexity, one of the issues about this conjecture is that if people proved that P equals NP, it's still possible, it's an open question, it might possibly be equal to NP, basically half the material at least of this course would just disappear, because a lot of it really depends on is going to depend on P not being equal to NP. I mean, we'll come to that many times as we come to it. We're going to often have to make assumptions that P is not equal to NP.
So NP stands for non-deterministic polynomial time.
That's exactly what it stands for. Yes, non-deterministic polynomial time. That's what.
I thought it stood for non-polynomial time.
Ah, no. So there are. No, it stands for non-deterministic polynomial time. So we'll see there are some non-polynomial time problems that are definitely not in NP, for example. One can prove that NP is not everything that's not polynomial time. Okay, but we'll leave those things for later. So what I want to now do is consider some examples. So it's about time for examples. So let's look at some problems in NP. Now, the way so the definitions have been about looking at words over an input alphabet, sigma, and accepting or rejecting words. But normally when you see problems described that are problems, computational problems, either in P or NP or in some other class, they're not described as, here's a set of words, can we accept this, can we recognize this language or not? They're described in nicer terms as some natural mathematical problem. Can we solve this problem in polynomial time or in non-deterministic polynomial time, rather than a set of words? And as I already said in I think the first lecture, or at least last week, the Turing machine model, because the Turing machine works with a tape, with an alphabet, in order to fit things into the Turing machine model, one needs to code up problems as words or as sets of words. And this is not such a hard thing to imagine nowadays, because we're familiar with solving problems on computers, and fundamentally we're representing everything on a computer as words over the binary alphabet 0, 1. So we're familiar with this kind of thing. But what I want to do is I'm going to give one example where I'm going to present a mathematical problem, and then I'm going to say explicitly how we code it up as a problem about languages, so that we've done that in one case properly, where we really see it as a problem about words and languages. And then I'm going to, after that, say, well, if we want to do the hard work ourselves, we sort of know how to do it, to code things up as problems about words. But I'll just then, henceforth, following that, present things in just more natural mathematical terms. And if you want to try to code it up as problems about languages, then that's a good thing, a good exercise for you to do. It'd be good for your soul or something to do that. But so for the first one, I'm going to go to all the trouble of actually coding it up as a problem about words. So first example. It's called the independent set problem. In set. And so I'm first going to present it in mathematical terms. And we're typically going to present problems like this. I'm going to say what the input is. And then I'm going to say what the question we're trying to answer. It's going to be a yes/no question. So do we accept, or that's yes, or do we reject? So the input in this case is a finite graph. And an integer, a natural number, k, less than or equal to the size of the graph. The size of the graph is, by this I mean the number of vertices of the graph. By the way, I mean, for those of you in the room, hands up if you know what a graph is. Okay, good. So just for clarity, so for this particular, there are some different notions of graphs. So for this particular question, a graph is a set of vertices together with a set of edges between different vertices where an edge has to be between two different vertices, and edges are not oriented. So there's a notion of directed graph in which edges have an orientation, but in this case, an edge, if you've got an edge from A to B, then that edge is also from B to A. Okay. And the question is, or the problem, is, does G have an independent set of size k. So an independent set in a graph G is also known as an anti-clique. Let's write this in blue. An independent set or anti-clique is a subset I of the set of vertices of V. This is the set of vertices of the graph. So V is the set of vertices such that for any two different elements of I, there is no edge between those two. So there are no edges between any of the elements of I in the graph G. So such that for every V and V prime in I, there is no edge from V to V prime in G. So there's no edge. Okay. And a clique, the opposite of this, is a subset K, let's say, capital K, such that for every pair of vertices in the set, there is an edge between the vertices. And so what we're asking for here is we're asking, can we decide this by some Turing machine that when we code up this input as a string, we'll accept in the case that G has an independent set of size K, and we'll reject in the case that G does not have an independent set of size K. So let's code this up as a problem about words. Now in the textbook always uses the alphabet consisting of just 0 and 1, just binary bits, which is perfectly fine, because if you use a larger alphabet, you can encode a larger alphabet using, for example, if you have 8 symbols in your alphabet, you can code each of those 8 symbols using 3 bits, for example. So there's no loss of generality in coding, in doing what the textbook does and coding up problems using the binary alphabet. But if one's actually defining encodings, which the textbook doesn't do in general, and which I won't do very much following this example, it's convenient to have a few more symbols around. So I like to have more symbols in my alphabet potentially, and I'm going to, in this case, it's completely unnecessary, but I'm going to use over the alphabet. I'll give us 0 and 1 because they're always handy to have around. And I also like to have some punctuation. So I'm going to give us a comma in the alphabet. So these commas are defining the set of, sorry, this is the alphabet. This is sigma. So let's do it. An equals colon. So I'm defining sigma to be this set. The set contains 4 symbols. One is a comma written like this, and another is a semicolon. So 2 different forms of punctuation. And I'll explain how we're going to encode the input by giving first an example and then the general recipe. So example encoding. So suppose the graph so the input is a pair consisting of a graph and a number. So let's look at a particular graph. And let's give the vertices numbers 1, 2, 3. And suppose it's got edges here. And so this is G. And this is little k here. So I'm asking, does this graph have an independent set of size 2?
Yes.
Very good. What is it?
1 and 3.
Indeed. So 1 and 3 is an independent set of size 2 because there are no edges between any two elements of 1 and 3. Okay, but the point is not actually in this case to answer the question, but to say how I'm encoding this as an input. And now we can represent a graph in general by what's called its edge matrix or incident matrix or transition matrix, depending on which terminology you use, and there might be a different one. So we'll represent G firstly as an edge matrix. So the edge or the adjacency matrix, I think that's what people normally say. The adjacency so any graph can be encoded as a square matrix where the number of rows equals the number of columns, because it's a square matrix, equals the number of vertices in the graph. And the idea is that in each row column, so sorry, here I'm just numbering them, this is going to be a 3 by 3 matrix because we've got 3 vertices in the graph. And in each row column position, you put a 1 if there's an edge from the vertex to itself. Sorry, not to itself, but the vertex that labels the row to the vertex that labels the column, and a 0 if there's no vertex. So such adjacency matrices for these kinds of graphs, they always have a diagonal of zeros because there's never an edge from the vertex to itself. And then the remaining things, well, we've got an edge from 1 to 2, so there's a 1 here from 1 to 2. It's a symmetric matrix because there's also then an edge from 2 to 1. There's an edge from 2 to 3, so there's a 1 here. And there's no edge from 1 to 3, so there's 0 here. And then we represent GK using the string. So we're going to represent the adjacency matrix using a string where we just have each row. We just read it off as a sequence of bits. We then use a comma to mark the end of the row, a semicolon to mark the end of the matrix. And there's some redundancy here. One doesn't need so much information, but anyway, it doesn't harm us to have it. And then we're going to put the binary representation of K afterwards using zeros and ones for that. So we represent this input as the string so 0, 1, 0, that's the top row, comma, end of row 1, 0, 1, comma, 0, 1, 0. We're now on the bottom row. Semicolon, it's the end of the matrix, not just the end of the row, but the end of the matrix. And then K was 2. So the binary representation of 2 is 1, 0. And that's enough. The blank space following this on our Turing machine can tell us we've got to the end of the input. Okay. So in general, G of size m That's the number of vertices. Represented by. So let's say A11 through to A1M, comma, A21 through to A2M, comma, dot, 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 to AN1 through to ANN.
But I think you made a mistake on the first row, A1M.
Of size M, so I've made a mistake in the second row. Yeah. Sorry, I've changed my M's to N's. The reason I'm using M rather than N is because I'm going to, where possible, I'm going to try to reserve N for input size. And so this is the input size here is not M because the input is a bit longer. And now we have the binary, and then here we have the binary representation, let's say B1 through to BL. Where this part here, this is the adjacency matrix. And this is the binary representation. I'll just write rep dot of the number K. And what is the input size here? The input size can anyone work it out in terms of M and K? Yeah, right. So yeah, pretty much. So it's M squared for all the A's plus M for all the punctuation, plus the floor of log 2 of K, that's plus 1. That's L, because the number of bits you need is log 2 of the number plus, if you just use the ordinary binary representation. So for example, 102 requires 2 bits and log 2 of 2 is 1. So you need to add 1 to the number of, to the binary log. So the input size in this case is M squared plus M plus the floor of the binary log 2 of K. So the textbook uses log for binary log 2. I don't like doing that. I like to use LG because log kind of has other connotations as a mathematician. So so in this course, I'm going to use log base 2. I'm going to use LG for log base 2. And I'm going to use LOG only in contexts where the use of the logarithm is base independent. So for example, in big O notation, big O of log, as you did in the exercise class, the O of log n, it doesn't depend on the base, it's the same. So if I'm using a specific base, I will use ln for natural log, LG, which if we ever need it, I don't know, LG for log base 2, log sub 10 to be clear for log base 10, which I very much doubt we'll need. Anyway, I forgot the plus 1. I want this to be blue. Sorry? Thank you. Okay. Right, so we've represented the problem. We still haven't completely shown that this class is in NP. So normally there's going to be a sort of seminar last hour, but this week there's not really a seminar. It's more of a third hour of lecture. Next week there'll be more of a seminar third hour, and 2 weeks on, the week after that is November the 1st, so the break. November the 8th, I'm planning to have the first student presentations. I still haven't got the schedule up, but I'm going to get that up this week, and I'm going to send you an email and ask you to sign up. I'm going to allow you to present in pairs or individually as you prefer, but there'll be more information about that sent by email. Anyway, it's basically 10 o'clock. We'll start again at 10:15, and so please, you can go on the break. I'm going to just stop the recording. There we go. Right. So I'm going to hopefully make this a short last hour, because I have a medical appointment, and in any case, in general, I want to have the last hour as a seminar thing. This I'm tending to. The last couple of weeks I've been overspilling the lecture into the third hour, and I'm doing the same again today. But I mean, today I don't have any seminar material anyway. So what I want to do is finish this example, have a different look at the class NP from the perspective that this example will give us, and then maybe give some more examples if we've got time. Otherwise, I'll leave the other examples for next week. So we're looking at the independent set problem. So the input was a graph together with a natural number that's less than equal to the number of vertices in the graph. We're asking, is there an independent graph? Is there an independent set of that size? For a graph of size m, we're representing this as a word over the alphabet of 0 and 1 and the comma and the semicolon of size m squared plus m plus the floor that this notation is. So that's the largest integer less than or equal to the floor of the log to the base 2 of k plus 1. And so I'm going to use some notation which we'll use in general. We'll use these corner symbols like this to mean the encoding of the input of the problem, if you like. So we write this for the word encoding G and K. Encoding the input GK. And what I'm going to show is that this problem is in NP. And what that means in language terms so what this means in language terms, I dot E, id est, that is. So what we mean when we say this problem is in NP, it means the set of words encoding inputs for inputs that positively satisfy the question, so for which the answer is yes. That set of words is a language in NP. Okay, so i.e. the language consisting of all input words in which G and K, in which G together with K, well, the graph G does have an independent set of the size K. So the language L, we could even say L in set, because it's the particular language to do with the problem in set, which we define to be all those words in over the alphabet we're considering. So 0, 1 together with a comma, looks like a G, but it's a comma. I'm just distinguishing it from the comma separators of in the set. So that the set of all words, so that's such that W is of the form so W is indeed the encoding of a correct input. Where K is less than or equal to the size of G. And we're interested in the language of those inputs in which the graph does indeed have an independent set of that size. So the point is we encode it as the set of all input words that satisfy the question. So where K is less than, and G has an independent set of size K. So this language, this set of words, belongs to NP. So I want to give you a little argument for this to explain why this is a non-deterministic polynomial time decidable language. So why this belongs to NP. So we want to argue that there is a non-deterministic Turing machine that decides this language, where the worst case running time is polynomially bounded. The worst case running time over all runs is polynomially bounded. Now, I've given the explicit encoding as a language. One could go a stage further. I could then also give you an explicit definition of a Turing machine. And in this case, it's not actually that of a non-deterministic Turing machine. It's not actually that hard. For almost all the other examples we're going to consider, actually giving the Turing machine itself would be a lot of work. You can always do it, but it would be really a lot of work. In this case, it would be a feasible thing to do. If I spent half an hour doing it, I would be able to define the whole Turing machine. But I think we don't want to spend time doing that. So I'm going to argue at a high level that such a Turing machine exists, but you should think about, particularly in this case, you should try to think about actually how you would define the Turing machine, the non-deterministic Turing machine itself. So I'm going to just outline the construction of a non-deterministic Turing machine. Outline of a multi-tape I mean, it can be probably two-tape, but you might use some other tapes if you want to as well. A multi-tape NDTM that decides L. So we're looking for the existence of an independent set, and we can represent an independent set. So the graph, if we've got the input, so suppose we're given an input of the form A11 up to A1M, comma, ... Then we know that the graph is of is of size m, has m vertices. Okay, this is the first comma. And we want to find a subset of k vertices. But what we can do to begin with is just guess a subset of the m vertices, and then we can check that it has size k, and then if it has size k, we can check if it's an independent set. So we're going to use non-determinism to just guess some arbitrary subset of the set of vertices. Then after that, we'll check it's the right size, and then if it is the right size, we'll check that it's an independent set. Or we could do that in the other order, it doesn't matter. So what we do, we've got the first comma gives us the number of things we need to guess. So we then use non-determinism. We'll use non-determinism. To non-deterministically choose right m symbols from 0, 1 on the second tape. So the point is, we just go into a non-deterministic little loop that m times we make a non-deterministic choice between 0 and 1 and write it on the second tape. So e.g., we get 0, 1, 1, 0, 0, 0, 1. M, so there are m such things on tape 2. But the point is the non-determinism is choosing these digits, right? And we can do this very easily because we can move the head along the input tape until we get to a comma. Each time we see a new input character, each time we see a new input character here that's not a comma, we non-deterministically choose the 0 or 1. And then when we get to comma, we stop, okay? So then we've got m different bits on the second tape. And the point is, we're using this to represent a subset of the set of vertices. So this one means vertex 1 is not in the set, vertex 2 is in the set, because here it's 1, vertex 3 is in the set, vertex 4 is not in the set, vertex 5 is not in the set, vertex 6 is not in the set, all the way through to the last vertex, vertex m is in the set. So this represents a subset of the set M of vertices. So like the textbook, I'm going to use square brackets M to mean the set of positive integers from 1 to M. Okay, so we non-deterministically guess a subset of the set of vertices. Then, once we've done that, that's all the non-determinism we need. Once we've done that, we check to see if the number of ones there corresponds to the number that's written in binary in the binary representation of K. And we check to see if the vertices picked out by this subset are an independent set. By for each of these, whenever we've got a 1 here, we go to the relevant row and the relevant position in the well, we need to go through, we need to take the positions 2 at a time out of here and go to the relevant row and column. But you can see that one can do that hopefully in polynomial time of computation, because here we've taken m steps. Oops. So that's, well, so we check that this subset has size k. And we check that this subset is an independent set. So to check it has size k, one way to do that is to go through this string that we've generated and make a counter that will increment in binary as we go through. Each time we get to 1, we increment our counter in binary. And when we get to the end of this string, we then compare the counter we've counted in binary with the binary representation of k. And so to do that, we're counting through here in binary. That's going to take O of m, plus then checking that it's the same as k. That's O of log 2 of m to check that. So the whole thing is O log m. So this part takes O of m. This part also has taken O of m. So this part here has also taken O of m. Then checking that it's an independent set. Well, to do that, we need to go through all pairs of places of positions that are so every pairs of vertices in the set. We need to check that for every such pair of vertices, there is no edge between them. We need to look at the relevant place in the table for the array. So going through pairs of elements in an n, we've got an m element sequence going through the pairs, that takes O of m squared. This is like a double for loop. And for each one, we need to check the relevant place in the representation of the array. That means going through the array each time. So each time we do that, we might need O of m squared to position on the array. We could be a bit cleverer about that by making sure we do things in a sensible order, but let's not bother. If we're very naive about this, we go through every pair, and for each pair, we just look up in the representation of the array, go through the whole array. That's for each of the m squared times, we're going through the whole array, which is O of m squared. So this is at worst O of m to the 4. But one can do it much cleverer, but we only need a polynomial time bound. So here, if using the naive algorithm, one can be cleverer here. And so overall, if all checks are okay, accept, else reject. And so overall, this is big O of m to the 4. But actually m is the size of the graph. And m was the square root of the size of the input. The input was m squared plus something, was m squared plus m plus log m, etc. But m is basically the square root of the size of the input. So that's i.e. the big O of m to the 4 is quadratic in the size of n. This is certainly polynomially time bounded. Polynomial time bounded. And notice that this works as it should, because if there is an independent set of size k, there will be one set of guesses, or at least one. There might be several independent sets of size k, but there will be one set of non-deterministic choices that gives us the relevant set. And for that set of non-deterministic choices, when we come to the deterministic part of the, so I should have said this part is deterministically. When we come to the deterministic part, then the subset will indeed have the right size, and it will indeed be an independent set. So if there exists an independent set of size k, one of the non-deterministic choices will find it. So one of the runs is okay, does accept as it's supposed to. If there is no independent set of size k, well, then none of the runs will be able to find it. So all the runs will end up in the reject state. So it does what it's supposed to do. It decides the language. It's a non-deterministic algorithm, and it's polynomial time bounded. So the language is in NP. The other thing to comment on is, as you can see, one has to be very, very lucky to get the accept result to come out. Whoever's responsible for the non-deterministic choice needs to make the right guesses. This is why this is not a realistic model of computation. You need some angel in heaven or something guiding the non-deterministic choices that's going to make the right choices. If you did it randomly by tossing a coin or something like that, you almost certainly wouldn't find, you'd have to be very, very lucky to get it. So it's not a realistic model of computation in that sense. We can't execute it. Okay, are there any questions on that? Good. Right, so that's the independent set example. So before going on to the other examples, that independent set example, the non-deterministic algorithm we found was of a very particular kind. It was somehow guess the information we want and then verify that it is correct. And in fact, every non-deterministic polynomial time problem, all non-deterministic problems can be put in that form. And that gives us an alternative definition of non-deterministic polynomial time. And it's actually in some ways nicer in this form. So I'm going to put this down as a proposition now, or theorem if we like. So this is what's called the certificate characterization and it's actually this theorem in the book. This is the definition, and in many ways it makes sense to have this as the definition. This theorem is the reason that NP is an interesting class more than the definition. The definition in terms of non-deterministic Turing machines is a little bit less interesting, I would say. The certificate characterization of NP is the following are equivalent. For a language, that's a set of words over an input alphabet. Firstly, sigma is in NP, or we just say sigma is NP. It is an NP problem.
Is that signal?
Oh, that's L. Sorry, yes. Thank you. The language L is NP. Yeah. And secondly, the idea is this, that problems in NP can be seen as they're problems for which we need to find a solution that we don't have to hand. We need to find some information that we don't have to hand. So in the case of the independent set problem, that information was an independent set. And they're characterized by the information we want is the information that if somebody gives it to us, we can easily verify it to be correct. If we've got a graph, if somebody gives us an independent set, they say, right, these are the vertices in the independent set, we can easily check that they're right, that that's an independent set. In the size of the independent set, we just need to do a quadratic amount of verification, just look at all pairs. Actually, all pairs only in one orientation, but that's still quadratic. So it's easy for us to check a purported solution is correct. But it's not easy to find the solution. That's the problem. It's not easy to find the independent set. So the NP problems are problems for which we can efficiently, that's in deterministic polynomial time, verify a solution if one is presented to us. So how could we say that? Well, we say we need to be given some certificate that the problem is in our class. So a certificate will be something that's not too large so that we can in polynomial time verify that it's true. So we ask for there to be a polynomial. P of n, such that, and we'll base this on natural numbers. For any input W in from the input alphabet, for any input word, the following are equivalent. I missed something crucial out. I think I'll write it down and then explain it afterwards. So there's a polynomial and a deterministic Turing, a deterministic polynomial time Turing machine. M such that for any input in the input out and the input language, the following are equivalent. So TFAE is the following are equivalent, as written at the top there. Maybe just abbreviate it here so it's clear. So firstly, W belongs to the language L, and B, there exists a certificate, which I'll use V for, which is, we'll use the input alphabet for it, but it belongs to sigma. So V is a string of length P of n. Such that M accepts the input WV. Okay, so the idea is in order to verify that a problem belongs to the set of words we're interested in, satisfies the condition we're interested in, we've got a deterministic way of checking if somebody gives us a polynomial, if somebody gives us a suitable certificate, then we can verify that the word belongs to V, the word W belongs to L using the certificate V. So in our case, the certificate the certificate was this string here that of length m that specifies the independent set. And now actually m here is some complicated function of the input length n, which involves a square root and is not quite an integer polynomial. But in this case, we could pad out the certificate by saying, well, let's make the polynomial size n if we want to. Doesn't hurt us to be given some more information, and we'll just use the relevant amount of information from it. But the point is, we're looking at problems that if we're given some more information, we can verify that our instance W satisfies the problem, satisfies the condition, if we're given the more information V. And we can do that efficiently. And to make sure it's efficient, we have to make sure that V does not contain too much information. So we make sure that the size of V is polynomially bounded in the size of W. Sorry, N here is a bit ambiguous. So N should be the size of the word W here, the length of the word W. Sorry. And so the nice way of looking at it is if we look at the P equals NP question using this definition. So we're thinking of P as those problems that we can efficiently decide. And NP is like those problems that we can efficiently verify a solution for if we're given some additional information to help us. And so P equals NP is it, if a problem can be efficiently verified, can it be efficiently solved? So the NP problems are those we can efficiently verify if somebody gives us some additional information. And can any such problem that we can efficiently verify, can we also efficiently, as it were, find the missing information? And that's the open question, whether or not we can do that. So is verifying a problem equivalent to solving a problem? So if P is not equal to NP, verifying a problem is strictly easier than, sorry, problems that are verifiable, efficiently verifiable. So yeah, problems that can be efficiently solved. There are some problems that we can efficiently verify, like potentially this independent set problem that we cannot efficiently solve because we don't know how to efficiently find this certificate. So I should say here, V is called a certificate. A certificate that W belongs to L. Okay, well, so I've got some more examples to give, but I think I'll save the examples for next week. I do just want to say something about the proof of this theorem. But I don't want to give it in detail. I just want to give it at a very, very high level. So we want to show that if a problem is in NP, then there's such a polynomial verification procedure. And if a problem has such a polynomial verification procedure, then it's in NP. So let's do 2 implies 1. So if we have the verification procedure, then the problem is in NP. So if you've got the verification procedure, the information we need, we're given an input word W. We want to check whether it's in the language L, and all we need is to get a certificate for it and check that that certificate is a certificate for W being in L. So basically, this is the same kind of algorithm that we followed for independent set, where we started off by guessing the certificate. That's what we did. With independent set, we started off by guessing a subset and then checking that it was a certificate. So 2 implies 1. It's basically the same idea we already had in our non-deterministic Turing machine for independent set. We first non-deterministically guess the certificate. The certificate. And this is, well, the amount of time that takes. The length of the certificate is given by the polynomial p in the length of W. So that's O of P of n, to guess P of the length of W many characters, and then verify. So and then use V, the certificate V, then use V to verify that W belongs to L. And this is, and the amount of time that takes is the polynomial that bounds the running time of the Turing machine M. So this is big O of time of n, which is also polynomial. And the total running time is the sum of these two, which is just whatever the larger of the 2 polynomials is. So it's certainly polynomial time. And in the other direction, 1 implies 2. So the other direction we're looking at, if a problem has a non-deterministic Turing machine that runs it, then we can instead, so if you've got a polynomial Turing machine that recognizes a language L, can we convert that into this witness form? So we do that we use the non-deterministic choices made by the Turing machine as the certificate. So each place there's a non-deterministic choice, then there might have been like 5 different choices. So it'll either take option 1, option 2, option 3, option 4, or option 5. And we simply code the sequence of such non-deterministic choices using the certificate. And the number of non-deterministic choices is bounded by a polynomial. So the certificate is polynomially time bounded. So use the sequence of non-deterministic choices. So if we can convert the non-deterministic Turing machine into a deterministic one by asking for some additional input, the certificate, which tells us what to do at the how to resolve the non-deterministic choices. And then it becomes deterministic. Whenever we get to a non-deterministic choice, we look at our instruction in the certificate and we go that way. So use the sequence of non-deterministic choices, non-deterministic choices as the certificate. I think that's enough information about that. Okay, well, that's everything I've got time for today, so I'm going to stop the recording